Hello, my name is Raihan Radzuan. My number matric is B012010136, and I want to explain about for electrical and electronic engineering laboratory for the part A. This is a module 2 for the introduction to digital logic circuits, binary adds, and flip-flop. For the part A, I want to introduce to basic gate and integrate circuit. To find investigate the logic gate operation, to use test equipment to detect the operation of IC logic gate. For part 1, they have given 5 IC here. So we need to know the output for the 5 IC here. They have 7400 IC, 7402 IC, 7404 IC, 7408 IC, and 7432 IC. Okay, for the 7402, the features is they have 4 independent to inputs, NOR gates, output directly interface to CMOS and NMOS and TTL. TTL means transistor logics, and the large operating voltage range, wide operating conditions, and not recommended for new design is 74LS02. And we look at for the 7432, they have 4 to input logic OR gate. The output directly interface CMOS and NMOS and TTL. It's the same like 7402, and but the difference is a diagram here. Let's see 7404. 7404 is logic inventor chips. The key applications area for 7404 hex inventor chips, mostly used in general applications on appliances that use logical inventor, memory units and storage applications, PC and notebooks, various digital electronics, networking gadget and system, and digital system. And we look at for 7408. 7408 is a logic gate chips with a 4-to input and AND gate. So the key application area for these chips is electronic device, digital electronic projects, digital system, networking, memory units, general purpose and logics operations, measuring instruments, service and ALUs. For the 7400, it means a NAND gate here. A NAND gate is actually a mix of NOT and AND gate when both of its input and function are at logic 1. Output is a NOT gate output, which is 1. The output from a NOT gate, it will be 0 volts is in response to a 1 input signal or plus input, meaning output will be logic 0 when input is at plus level. So that's for 5 IC here. So we need to do in software QCS. So I open it to Q. For the first step is we need to click digital component and find is 7400. That means it's a NAND gate. So this is a NAND gate here. Okay, and we need to put source to make it run 1 and 2 because they have two input here, and the output yes just 1. So put it little circuit here, and you need to rename it. This is output, and this is source A, and this is source B. We need to put digital simulate to find the tabula circuit. Tabula. So this is the digital simulate. Try to emulate here. Be patient and you can get here. Diagram truth table. Okay, we find the truth table here. Click A and B and for the output here, and you can get the truth table, the data here. To try to make it bigger so we can see the output here. So this is the output for source A and source B here, 0 0, and you can get output here 1. For 1 0 you can get 1, 0 1, and you can get 1, 1 1, you can get the output is 0. To make it simple, clear, I already done it for 5 IC. So I already explained about 7400 for NAND gate, and I will to explain about 7402 IC for NOR gate. So this is the symbol of the NOR gate here, and you can get the data here is the output, and you can get the source A and B 0 0, and you can get output 1 1 0, and you can get 0 0 1, you can get 0 1 1, and you can get 0. For the 7404 IC is a NOT gate. They have one source and one output. So this is the diagram for the NOT gate here. They have one source, so that means the output is 1 and 0. For the 7408 IC, that means it's an AND gate. So this is the symbol diagram here. They have two sources. So this is the truth table. 0 0, the output is 0. 1 0 is mean 0. 0 1, the output is 0, and 1 1, and you can get the output 1. For the 7432 IC, it means OR gate. This is the diagram here, the diagram for OR gate, and you can get the data here. 0 0 is mean the output is 0. 1 0 is mean the output is 1. 1 0 1 is mean the output is 1, and 1 1, and you can get here is 1. So this is the single 5 IC here is a single. I don't put together. So that's all for part A. This is for part B, simplifications and combinational of logic gate. They have given 4 IC here, 7400 IC, 7408 IC, 7432 IC, and 7402. We need to find the output of F here, the truth table. So they have given the logic circuit for figure B1. We need to put the diagram, the component, to find the truth table. So this is the part B, the circuits for the figure B1. I already put together here. So I will explain. This is a 7400. It means it's NAND gate. This is a 7432. It means OR gate. This is the 7408. It means AND gate. And this 7402 it means NOR gate, and this 7432 it means OR gate, and this is inventor in software cubes. That means it's 7404 is NOT gate. So put it source 1, 2 and 3 source, and put it name here is this input A, B and C. So this is the output of F, and we need to put digital simulate here to find the truth table. So and already finished. Try to emulate, and we need to be patient. Okay, this is okay. We need to find the truth table here. This is truth table. They have 3 input A, B, C, and we need to click 1, 2 and 3, and then we need to find the output here. So they have so this is the output here, and make it bigger. So they have 1, 2, 3, 4, 5, 6, 7, 8. So this is the input, 3 input and 1 output here. For the first one is 0, 0, 0 is mean 1, 1, 0, 0 is mean 1, 0, 1, 0 is mean 1, 1, 1, 0 is mean 0, 0, 0, 1 is mean the output is here is 0, 1, 0, 1 is mean 0, 0, 1, 1 is mean 1, and the last one is 1, 1, 1 is mean the output here is 0. So that's all for the part B. Thank you for me.
Hi, my name is Shin Nee, and now I would like to show how to construct the binary adder. There are 4 types of adder, which is half adder, full adder, 2-bit ripple adder, and 4-bit parallel adder. So for the part 1, which is half adder is a combination logic circuit which is combined with 1 XOR gate and 1 AND gate, and there will have 2 input, and it will generate out 2 output, which is sum and carry. So right now we need to search the circuit for the half adder. So this is the circuit for the half adder, and after we get the circuit, we can start to construct it in the software. So for first, we need to take out the digital component, which is the XOR gate, and then AND gate, and then we need to put 2 digital source as the input because they got 2 input, and then we start connect it by using wire. After we done connect, we need to label it by using wire label. So this is the A input, and then here is the B input, and this will be the sum output, and this is the output of carry. After we done this, we need to add on 1 digital simulation so that we can simulate this digital circuit. So we click on simulate and save it, and it will start to simulate. After done simulate, we add on the truth table, and we select the output so that we can see the output for it. So this is the truth table for the half adder. When the A and B is 0, it will get 0 sum and 0 carry, because when 0 plus 0, it will get nothing. For the 0 plus 1, it will get 1, so it will become the sum, and same as the 1 plus 0. For the 1 plus 1, it will become 10, and the 1 will become carry. So this is how the half adder function. Next, part 2, which is full adder. Full adder is a combination logic circuit with 2 XOR gate, 2 AND gate, and 1 OR gate. And they will have 3 input, and it will generate out 2 output, which is the sum and carry. And full adder also perform as a digital addition for the 2 digital number. So right now we need to find out the circuit for the full adder, and this is the circuit for it. And after we get it, we can start to construct it in the software. So first we need to take out the digital components, which is the XOR gate. We need to take out 2 because they got 2s. And then we need to take out 2 AND gate and 1 OR gate. And then we need to add on 3 digital source and we connect it by using wire. After then we done how to construct this circuit, and now we need to label the wire. So this is the A input, and then this is the B input, and this is the C in, and here is the output sum, and here is the carry. And now we need to add on the digital simulations, so we can simulate this circuit. And then we click simulate and save it. After that, it will start to simulate. And now we choose the truth table and then select the sum and carry, so we can know about the output for it. So it will be same like the half adder, and also will be same like the digital addition. When 0 plus 1, it will get 1, and then 0 plus 1 plus 0 also get 1. For those 1 plus 1, it will become 10, so it will become carries, and the 1 plus 1 plus 1 will become 11, so it will have 1 in carry and also 1 in sum. So this is how the full adder functions. Next, part 3 is about 2-bit ripple adder. 2-bit ripple adder is a combination of half adder and full adder. And from this sheet, we can see that it wants us to connect it according to the diagram below. So we can see that the C out of half adder is go to the C in of full adder. So right now we draw it in the software. First we copy the circuit of half adder, so we no need to draw it again. And then we also copy for the full adders. And then now we change the C in for the full adder. So we connect the C out of half adder to the C in of full adder. And then we also need to change the label of this all input. So for the half adder, we need to put A1 and B1 for input. And the output sum is 1. And then for the full adder is A2 and B2. And then sum is sum 2 and carries is still same. And now we done the connections, and we can add on the digital simulation so that we can simulate this circuit. So we save it in, and then it will start to simulate. After simulate, we choose truth table to show the bullet expressions. So we need to look like this. So the input will start in A1 first. So we need to put A1 at behind, and B2 also same. And then is carry and sum 2 and sum 1. So we can see that this is the truth table for this circuit. When the input of half adder is 0 and 1, it did not have carry, only have sum. And then the A2 and B2 is 0, then it will not have sum or carry, so it will only get sum 1. And for these 2-bit ripple adders, it will also assume as a digital addition. For example, like this, 10 10 plus 00 equal to 10. For 11 plus 01, it will become 100. So this is how the 2-bit ripple adder functions. Last part 4, which is about addition and subtraction. When 4 adders is combined together, it will become a digital addition for 4-digit numbers. So first we need to find out the circuit for 4-bit parallel adders, which is like this. And now we know the circuit, and we can start to construct it in the software. So first we make sure that we can see that it have 1-bit full adders in the digital components, but because we don't know how the circuits inside the 1-bit full adder, so we use the traditional ways, that we use the circuit that we construct just now, and then copy and paste for 4 times because it needs 4 full adders. And then we need to change the connection for both C out and C in. So for the first full adder, C out will connect to the second C in, and then for the second will connect to the third, and the third will connect to the fourth. And after that, we need to change for the C in for full adder 1, because they mentioned that it will connect to ground. And then we need to change the label for it. For 4-bit adders, we need to make sure that it starts with 0. So there is A0, B0, sum also 0, and then the second one is A1, B1, Cin1, and then sum 1. For the third one is A2, B2, Cin2, and then sum 2. And then the last one is A3, and then B3, C3, and also sum 3. And now we've done all the circuit, and we can add on the digital simulation to simulate this circuit. So we simulate and save it. And then it will start simulate. So right now it's already done simulate, and we need to add the truth table for it. So we select the truth table, and then because the input is start with 0 and then into 1, 2, 3, so we need to read the value forward. So we need to put A3, A2, A1, 0. Same as B, we also put B3 first and then continue so on. And after that, we select the C out, also the carries, and same to the sum, we select 3, 2, 1, 0. So right now we get the truth table for it. So you can see that it is additions. Like for example, this is 0001 plus 0000, and then we will get 0001. And for the next example, we can take this 0011 plus 0001, and we will get 100. So this is how the addition function. And in the lab, they got call us to find out the digit by using binary addition. So right now we can write into change this decimal to the binary by using calculator. So I just pick one of them. For example, I took the second one, 6 plus negative 3. So the value of 6 is 0110. So I change it become logic 1 and 0. So I put it inside. And then it's negative 3. So negative 3 is 1101. So for the B, we need to change to 1101. So we delete all the digital source first, and then change the logic 1 and 0 inside. And then we need to change the digital simulation. From here, we need to change the truth table to the time list, because truth table is used for the digital source, while time list is used for the logic. And then Right now we can simulate it. So this is the answers when A is 0, 1, 1, 0 equals 6 and B is 1, 1, 0, 1 which is negative 3. So when it's timed together, when it's plus together, it will become the output 0, 0, 1, 1. So this is how we get the output and how it's function. Subtraction, it also same as addition that use a 4-bit parallel adder. So right now we need to find out the circuit for it, and from here we can see that the circuit for it is like this, and it got a little bit different with additions that in the input B it will have one inverter to inverse the value. So right now we already know the circuit and we can start to construct it in the software. So first we just copy and paste the addition circuit because we can save the time. No need to redraw it again. And then we change a little bit for it. So we need to add on the components of inverter at here at B. And after that we need to add back the digital source. It will become like this, and we connect it up by using wire. After done all of this, we need to add back the label B. This is B0, and then here is B1, and then here is B2, and here is B3. And we also need to change the Cin in the first full adder because in the question they want us to connect it with 5 volt, but in the digital components we did not have 5 volt, so I used logic 1 to replace it, and now we can start to simulate before at the digital simulation, and then we can start subtractions. And now it's done. Simulate, and we just choose the truth table, and same as the additions, we need to read from the forward, so we need to put like this. And now we done the truth table. So for example, I take 0001 minus 0001, it will get 0000. The next example, I take 0011 minus 0010, and it will get 0001. So this is how the subtraction function. And in the question, it's also called us to use it to calculate the decimal number by using it. So right now I will show one of the example for this. When 7 minus plus 5, so 7 is, we're using calculator to check the value 7, and it is 0111, So we change the value of A to become logic 1 and 0. So the first full adder is 1 because it read from the backward. So it will become like this. And the next value is 5. So we put 5. So we get 0, 1, 0, 1. So we change the input for it. So it will become like this. So right now we're done. And now we need to change the setting for the digital simulate to time list because it is used for the logic. And now we simulate it. And then the table will become like this. When 0, 1, 1, 1 minus with 0, 1, 0, 1, so we will get 0, 0, 1, 0. So this is how the subtraction function. And that's all for me. Thank you.
Hello, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Asyraf bin Suhaimi. The number metric is B0120101442. For this video, I want to present about my task for the experiment 2 digital electronic about part D flip-flop. For this, as we can see in the lab sheet, the flip-flop on the objective is to understand basic memory unit and to verify the operation of various type of flip-flop by using the respective IC and logic trainer. For the equipment, we use QCS QCS software to solve all the part. That's mean asynchronous RS flip-flop, D flip-flop, and JK flip-flop. Okay, we start first RS flip-flop. For RS flip-flop, I do the in QCS. There's no gates because the lab sheet we use must to do in NOR gate. This RS NOR gate and others is T flip-flop. This flip-flop and this is JK flip-flop. That's mean 1 J1 K1 and this JK flip-flop J0 K1. This JK J1 K0 and this last J0 K0. Okay, we can present on the words. Yes, I do. For the result, as we can see, that I get RS flip-flop. The set reset flip-flop, as known as the SR flip-flop, is made up of two NAND or NOR gate. For this lab, we use the NOR gate for the NOR gate, and next the operation is called transparent latch because the output part will respond to the input by locking the given input value as latch or remembering the input. As we can see, this is the RF flip-flop where the S0R0 I get QS and QBS. That's mean I don't know what I want to say because when I construct this circuit, That's get this value for the 0 and as 0 output 0. That's mean I put the latch. And that's as S0 R1 I get Q0 Q1. That's mean state in reset. Next S1 R0 I can get Q1 and QB Q bar. This QB is Q bar. That's I get in 0. That's mean the state in set. Next S1 R1 I get Q0 Q bar also 0. The instead in a stable. Then next we can discuss about the flip-flop. The flip-flop has a characteristic that will produce the same output as the logic on line D when there is a positive clock. If not, then the flip-flop is in a state of memory as a memory. That we can see this I do some a little modify for this circuit and value as on. Yes, we can see the graph of clock when low is rising, positive and negative and so on. And this we can get the D flip-flop when the low and high and low again. We can see the table where D equal 1, clock equal 1. That's mean rising 0 to 1. The output is Q1 Q bar 0. That's mean state in set. And a second is D0 clock 1, same as rising 0 to 1. The output is Q0 Q bar is 1. And in this state we can call the reset. That's all for the D flip-flop. The next is JK flip-flop. The JK flip-flop, yes, I can say JK is an ideal memory element that used as a counter, frequency divider, and register. For this JK flip-flop, we must do step by step. That's all. On the left sheet has many steps for this task to solve. For first step, we do the J equal 1, K equal 1. For the clock equal 0, that's mean low. We can get Q is 0, Q bar is 1. Then we put in clock equal 1, that's mean height Q1 Q bar 0. That we can see the this that's what I say truth table. We can see the output clock is 0, J1 K1 Q bar 0 and Q0 Q bar 1. This was clock 2. The same what I write this. And for this for next clock 1 J1 K1 Q1 Q bar 0. That's the same. I write this. Okay, we can see the timing diagram move as low, high, and low again, high again. For this is a clock because the number is condition for this 010101, and same as Q and Q bar. Okay, for the second step, we must do the J equal 0, K equal 1. Then for this second step, where clock equal 1 or clock equal 0 or 1, the value of Q and Q bar are same straightly. Where Q equal 0, Q bar equal 1. That's the same for the value even clock 0 or 1. As we can see for J1, J0, K1, Q0, Q bar 1. This is for the second step. Then we can see the time diagram is there. A movement when J is in low, K is in high, Q is low, and Q bar is in high. Okay, this is for the second step. Okay, we can go the third step. That's J equal 1, K equal 0. This we can get the clock equal 0, Q equal 0, Q bar equal 1, and Q clock equal 1, Q equal 1, Q bar equal 0. That's mean the for this step is same as first step value. Where Q0, Q bar when clock in 0, even the J K value is different, but the value for this Q bar is same as first step. Okay, for the last step in the fourth step, we do the J0 K0. That's mean clock 0 or 1, clock Q0, Q bar is 1. This is for the first step is same as second step where the even the JK is in equal 0, but this is same value as a second step, but the difference in JK only, where the J, you can see the time diagram, the J is on the low, K is on the low also. Then we can see the table where that I construct the input for the JK for this I choose the Q only for to read, where the J1 K1 the output is in the charge, or we can call the continuous charge, and for the state we can call this is a toggle. The next the input J is 0, K is 1, the output is 0. That means instead we can tell in reset to 0. The input next J is 1, K is 0, the output is 1. That means clock equal 1. Then the last input J is 0, K is 0, the output is 0. That means in the state we can see the no charge for the this JK flip-flop. Okay, that's me enough for me for this video. I hope for the video we can understand for the what we call RS flip-flop, D flip-flop, and JK flip-flop for this experimental mode digital electronic. For the all, thank you and goodbye.